In today's lesson, we will be solving addition equations. The goal of our lesson today is to use subtraction in order to help us solve these addition equations. Before we begin, it's going to be helpful for us to review some vocabulary that we're familiar with from a previous lesson. Algebraic expression should be familiar to us. For review, algebraic expression is a mathematical phrase that contains one or more variables in addition to the numbers and operation symbols. The key, or something new to us, should be that it has an infinite number of solutions. Solutions is just a fancy word for answers. So when we have an expression, we could have an infinite number of solutions each time that we try that out. So kind of to review what I mean by that, if we go back and review some of our examples of algebraic expressions, you may remember working with things like x plus 4 or 3y or m minus 8, could be 2m minus 8. In all of these expressions, when we substitute a value for x, we're given a multitude of different variables. So for example, if I look at my x plus 4 example, if I set up a chart and set my value of x as 1, I would have 1 plus 4 equals 5. If I decided that x should be 8, I would have 8 plus 4 equals 12. If I thought that x should be 2.5, I would do 2.5 plus 4 equals 6.5. Notice with each of the different values I choose for x, I'm going to get a different result. And that's where the idea that I have an infinite number of solutions or answers comes from. Our new vocabulary word is going to be an algebraic expression, which is simply a mathematical statement of equality between two expressions. So we're using those expressions that we had on the previous page in order to create an equation. We're going to have two of them. The idea is they're separated by an equal sign. It shows equality. Algebraic expression has to have an equal sign in order to be considered an equation. So that's important for us to remember. What else is new or different for us is that it has only one solution or answer. So whereas an expression had an infinite number of examples, an equation is going to have only one. So some examples of equations are going to be things like x plus 3, but then we need to show that idea of equality, so we'll say that that equals 15. Or we might say 2y equals 8. Or we might say 6x plus 2 equals 4x. Any combination of different expressions connected with an equal sign is going to result in an algebraic equation. And we're going to see over the next couple of slides why and how there's only one solution to each algebraic equation. The goal of our lesson today was to solve addition equations. So using the example x plus 2 equals 5, we're going to see just how we should do that. You may be thinking of the only value that makes this true in your head already, but I want to go ahead and show you how we go about solving such equations and the work that's required to do so and why that works. So whenever I look at solving an equation, I think about it as a balance scale like the one you see over here. Notice in a scale, the goal is always to get both of our sides balanced so that they both are at the same level and meet in the middle. That tells us that both sides weigh the same or equal the same. What we should think about that scale is where that equal sign is in our equation, that's like the middle of the scale, what we're trying to find balanced. So anything we see on the left side of the equation, the x plus 2, is going to be on the left side of our scale, and we want that to balance out or equal the 5, which we see on the right side of our scale. So that's why we have the 5 squares on the right side, comes from the right side of that equal sign, and on the left we have 2 boxes for the number 2, but we have in addition to that the letter x, an unknown, so I've shown that with a bigger box here. Now if I'm trying to find out what that missing value is of x, I can think about what I would have to do to get that x all by itself, because whatever's left on the other side will tell me what that value or what that x is worth. Notice if I take one of these boxes and move it off of this side, what's going to happen? Well, this side's going to be lighter, so it's going to go up, and this side is going to go back down because it's going to be heavier than the other side. Now remember, I don't want that to happen. I want both sides of my scale to stay in the middle. So if I take away one from this side, from the left side, I'm also going to have to take one away from the right side. Now I've met back in the middle again. But I still have that x along with one more box, so I'm going to need to get rid of it. I want to get x all by itself. So I'm going to take the second box off, but again I'm going to notice that this side will go up and this side will move down. I don't want that to happen, so to avoid it I'm going to take another box off of this side. Now all that's left on the left side of my equation is my unknown box. On the right side, I have 3 boxes left over, so the value of this x, this unknown number, must be 3 units. What that looks like in an equation is, I need to show exactly what I do to both sides. Here I took away 2 from this side of the equation. I had x plus 2, but I subtracted 2 from it. If I have 2 things and I take away 2 of them, I just have 0. So in essence, what I have left on this side of the equation is x plus 0. I always want to work on the left side of the equation and the right side. That equal sign is always like my border, my boundary between the two sides. If I take away 2 from this side, though, in order to keep it balanced or equal, I'm going to have to take 2 away from the right side of the equation. So if I do 5 minus 2, I'm going to get 3. Just like with order operations, I'm going to carry down that equal sign. So I now have x plus 0 equals 3. Well, I know that if I add 0 to any number, that number is going to stay the same. So I don't really need to write that x plus 0. I can just simply write x. I don't need to add 0 to it. That's understood. So my answer would be x equals 3. And if I go back, it's always important to check our answers. If I think in my head 3 plus 2, well, that equals 5, and that's what the equation says. So I know that I did a good job and correctly found that one value. Notice if I put any other value besides 3 in there, if I put a 4, I would have 4 plus 2 equals 5, and that statement's not true. 4 plus 2 would be 6. 6 does not equal 5, so the only value that will make that equation true is the value 3. Let's go ahead and try another example. It's going to become tedious to keep drawing a balance every time and pulling markers off each side, but if I remember that key idea that whatever I do to one side of the equation, I have to do the same thing to the other side in order to keep it balanced, I should be able to solve this equation without drawing an actual balance in 27 blocks and 92, because that's a lot of drawing. So what I'm thinking to myself is, if I have 27 things on this side and I want to get the x by itself, I'm going to have to take away 27 of them to bring me to 0. That 27 positive, my 27 things, if I take away 27 of them, I will have 0. So those kind of cancel out. I can take those off. But what I have to remember is if I took away 27 from the left side of the equal sign, I have to do the same thing from the right side. So what that leaves me is my x is going to travel down. So I have the value x, those 27's cancel it out, and my equal sign. And now I'm going to have to do some subtraction. I can't take away 7 from 2, so I'm going to borrow, make that 12, and I'll have 5 and 6. So my x should equal 65. Again, I can go back, and it's always important for me to check my work. If my x was 65, and I added 27 to it, I add those two values, and I get 92, which is exactly what I wanted to get. So taking the same amount away from both sides helped me figure out that x equals 65. After those two examples, let's take away the big ideas for solving equations with addition. The first thing we want to remember is we want to think of algebraic equations like a scale, like that balance. What that means for us is that whatever we do to one side of an equation, we must, so important, we must do that to the other side as well. Also, we must show our work just like we always do in math, we need to understand our thinking. So we must show what we do to both sides of an equation, just like I've done on each of those. I made sure that I took away the value from both sides. As long as we follow those big idea rules, we are able to solve equations that have decimal values as well using the exact same idea. As long as I take the same thing away from both sides of the equation, I'm not going to change its value. Instead, it's going to help me find the answer. So on this side, I notice right away, again, I kind of think of that equal sign as my middle, like I split my problem there. On the left side of the equal sign, I have x plus 1.2. So I need to get rid of that 1.2. I want to make x all by itself. So to do that, I'm going to have to subtract 1.2. If I have 1.2 things and I take 1.2 away, I have 0 left over. If I do that to the left side of the equation, though, I'm going to have to make sure I take it away from the right side. I know I can add that 0 without changing my value, so then I'm going to go ahead and subtract, and I get 7, 4, and 2. Have to remember to carry down my x and my equal sign, so x is going to equal 2 and 47/100. Again, going back to check my work, I know that if I take 2 and 47/100 and I add this 1.2, I should go back to my original answer. And if I go ahead and add, I notice I get 3 and 67/100, which is exactly what I wanted. So again, I notice that taking the exact same thing away from each side of our equation is going to help us find our value. If you feel like you've gotten the hang of this, please go ahead and pause the video, attempt this problem on your own, and then check to make sure you did the correct thinking. If you'd still like to see one more example gone through together though, just keep following along as we solve this problem. Notice we have, again, x plus 93 and 67/100 equals 189. If I want to get x by itself so I can figure out what it is, I'm going to have to take away 93 and 67/100. I do that so that they can cancel each other out. If I start with 93 and 67/100 dollars and I take away $93.67 to purchase something, I'm going to have 0 money left. Those are going to cancel each other out. But I have to make sure I take that away from the other side of the equation as well. So I can bring down my x and my equal sign, and if I find out what x equals, I'm going to have to do some borrowing in this example. So a good review of subtracting decimals. When I do that, I'm able to determine that the answer should be 95 and 33/100 since I took away the same amount, the same value from both sides. To check my work, I know that 95 and 33/10 plus, or hundredths, plus 93 and 67/100 should take me back to that original 189. If I go through and check my work, I do get 189 and 0/100, 0.0, which is the same thing as 189. And I see that by doing the same thing to both sides of the equation, showing all the work I did both on the left side and the right side. Very important that you show that these numbers cancel out. If I was to not show this side, if I were to just erase this part, that would not help me to show exactly what I was doing. I need to show what I do to one side of the equation, I must do to the other side. Both sides are really important. Now, at this time, I want you to take a look at the other examples on your worksheet and bring any questions and your work on those into class tomorrow. Thanks. Bye.